Hey there, how is it going? We are going to look at 5.3 today on inverse functions and relations. And so the objectives of this lesson will be to be able to find inverses of relations and functions and to be able to determine whether two functions or relations are inverses. And we've got a boatload of standards here that this will cover. ACE 4, solving literal equations, FIF 5, being able to relate domain and range to its graph, and then we're looking at a precalc standards, what this PC prefix is for. Understand that an inverse function can be obtained by expressing the dependent variable of one function as the independent of the other. F and G are inverse functions. Nice little typo there. We'll fix that later. If and only if f of x is equal to y and g of y is equal to x for all values of x in the domain of f and all the values of y in the domain of g. And find inverse functions for one-to-one functions or by restricting the domain. And we'll look at that in a couple of examples. And then 4a says be able to use composition to verify one function is an inverse of another. And so we talked about compositions yesterday in 5.2. So we're going to bring that back up today. All right, so as we look at this lesson, a couple of things that we're going to look at. So first, an inverse relation. Two relations are inverses if and only if. Now, let me talk about this if and only if for a second. You talk about it a little bit in geometry, but I want to reiterate it. This is a two-way street. And so if you ever see the expression if and only if, it means that I can talk about the first part and then the second, or I can have the second part and then the first. It's a biconditional statement. I can put the if first and the then second, or I can switch it and have the second thing as the if and the first part as the then. So two relations are inverse functions if and only if whenever one relation contains the element AB, the other relation contains the element BA. So we see that the ordered pairs are going to flip. The x becomes the y and the y becomes the x. And so let's talk about this with this first example here. The ordered pairs of the relation 2, 4, 8, 4, 8, 1, and 2, 1 are coordinates of the vertex of a rectangle. Find the inverse of the relation and describe the graph of the inverse. So we're actually I've got a graph here. So let's graph these 4 points on the coordinate plane. So as we plot these 4 points, we've got the ordered pair 2, 4, 8, 4, 8, 1, and 2, 1. And so we end up with this rectangle here. Now, if I'm going to find the inverse of this, all my x's and all my y's are going to flip. And so let's talk about these 4 ordered pairs. I'm going to change colors here so that way we see it in a different color. So what would 2, 4 become? Well, the x becomes the y and the y becomes the x. This would be the ordered pair 4, 2. So 4, 2. And then the next ordered pair from 8, 4 would become 4, 8. 4, 8. The next ordered pair 8, 1 becomes 1, 8. So 1, 8. And the last order pair 2, 1 becomes 1, 2. And so we end up here. So I've gone from this red rectangle here, that's long, to this blue rectangle that is tall. That's what happens with inverses. So this isn't a reflection across an axis. This isn't a flip or a twist. It completely changes my domain and range values in relation to one another. So what does the graph of the inverse look like? Well, it is still a rectangle. That has been switched from the horizontal to vertical. Now again, the ordered pairs don't line up, right? Like this ordered pair does not line up with this ordered pair here. Now they're related because this is 2, 1 and this is 1, 2. So there's a relationship here. And we're going to talk about that relationship a little bit later, okay? All right, so again, if you're looking at ordered pairs, just flip the ordered pairs. That's all you got to do. Don't make this more complicated than it is. If you're given a table of values, flip the x's and the y's, right? The x's become the y's become the x's. Don't overthink it. It's exactly what it's saying. The domain becomes the range becomes the domains, the x's become the y's become the x's. Don't overthink it, y'all. All right, so let's take a look at a property here. The property of inverses. If f and f inverse. Now, we're talking about this here, and normally a lot of you would say f to the negative 1 power. Well, that's actually read as f inverse. Don't say f to the negative 1. If f and f inverse are inverses, then f of a is equal to b if and only if f inverse of b is equal to a. So again, we see this switch of the x and y values. Now, the inverse of the function can be found by swapping the domain and range. That's exactly what we did in the first example with those ordered pairs. So find the graph and inverse. Find and graph an inverse, if I can say things correctly. So find the inverse of the graph f of x is equal to 2/3 x plus 6, and then graph the function and its inverse. Now, let's talk about how we find an inverse. There's a few steps to this. So step 1, write out the function, write the function with a y. So I'm going to write y equals 2/3 x plus 6. Step 2 will be to switch the x and y. Now, what I mean by switch the x and y is literally, I see y here, I'm going to write an x. I see x here, I'm going to write y. So I'm going to write x equals 2/3 y plus 6. Okay. Step 3. Solve for the new y. Okay. So now I've got that x is equal to 2/3 y plus 6. I'm going to subtract the 6 from both sides and get x minus 6 is equal to 2/3 y. And then I'm going to multiply both sides by 3/2 to get rid of the fraction on the y side. And so I'm going to end up with 3/2 x minus 6 divided by 2 is 3, times by 3 is 9, and that's equal to our y. The final step, write y as f inverse of x. And so our final step here, I'm going to flip the equation around. F inverse of x is equal to 3/2 x minus 9. Now, let's look at how these two graphs are going to look on the coordinate plane. We go back to the original function first. I'm going to graph it in orange. F of x is equal to 2/3 x plus 6. So I'm going to start at 6. That's my y-intercept. I go up 2 and right 3, up 2, right 3, and I can reverse back this way, down 2, left 3, down 2, left 3, down 2, left 3, and this is my line. Okay. Let's talk about what I found for the other one. F inverse of x is equal to 3/2 x minus 9. Okay, that's a 3 here. That's a 2. So I'm going to start at the negative 9, and I'm going to go up 3 and right 2. Up 3, right 2. Up 3, right 2. Up 3 and right 2, up 3 and right 2. And so what we see is this brown line here. Now, it may not look it, but these two lines are not parallel, and they eventually will cross one another. But let's talk about a couple of characteristics here. I want you to look at a couple of key points. What's the y-intercept here of the original function of our f of x function? And this is our f inverse down here. What's the y-intercept of our f of x function? It's 0, 6, right? This ordered pair would be 0, 6. Well, go back to what we did in example 1. If I'm finding the inverse, what's going to happen to that ordered pair? It's going to do what? Switch. So on the inverse function, I better have the ordered pair 6, 0. Same thing with the x-intercept over here, right? The x-intercept is negative 9, 0. And when I invert that, I'm going to get 0, negative 9. So again, doing an inverse is not about switching signs, it's about switching the x's and the y's and how they're related. All right, so let's talk about a way to know if a function will have an inverse function. Now, all relations have inverse relations, but that doesn't mean it's a function. Remember, a function is where every x has only what? One y, right? So a function has an inverse function f inverse if and only if each horizontal line intersects the graph of the function in at most one point. Now, go back to chapter 2. We talk about the vertical line test. We talk about in Algebra 1 as well. The vertical line test tells us if I draw a graph on the coordinate plane, let's say I've got this nice, beautiful x cubed function going through the coordinate plane, right? I can draw as many vertical lines as I want. I'm only ever going to touch the function once at any point. The horizontal line test tells me that I can do the same with horizontal lines, which means that the inverse of this function would also be a function. But if I were to draw a graph, let's say I draw a parabola in the coordinate plane like this. This is a function, right? Because it would pass the vertical line test. But would its inverse be a function? Well, down here it never touches anything, but when I get right here, like at the x-axis, it touches that red graph twice. And so the inverse of the red function would not be a function. It would be a relation because it would fail the vertical line test once I graphed the inverse. And so we get this statement here. It may become necessary to restrict the domain of a function in order for the inverse to be a function. And we're going to look at that in example 3. We want to find the inverse of x squared minus 3x plus 2, and then graph the function and its inverse. Now, this one gets a little interesting because we have the same rule of having to swap the x's and the y's and solve for the new y. Now, let me show you how that works for this problem. So y is equal to x squared minus 3x plus 2. And then we swap the x's and the y. So x is equal to y squared minus 3x plus 2. Well, now I need to get this, sorry, this should be a y. X is equal to y squared minus 3y plus 2. Well, this is a quadratic, so I can factor it. So x is equal to y minus 2 times y minus 1. Now, again, that comes from our x puzzle. I've got negative 3 and I've got 2. And so negative 2 and negative 1 will multiply. And I've got these numbers in the wrong spots. The 2 here and the negative 3 down here, right? Because our b goes on the bottom. These two will multiply together to positive 2. These two will add to negative 3. And so I get this statement, right? Now, does that get me any closer to solving this out for what might happen? Not really, right? Because again, I need to set that equal to 0 to be able to factor it and find the not x-intercepts of this, but the y-intercepts for this, right? Because we're not x plus something, we're y minus something, right? And so if I were to continue this out, what we're going to see is that this function is going to take a couple more steps to get this y by itself. And actually, it's actually not easy to get because it wouldn't be a function anyways. Because let's graph this on the coordinate plane first. So, thinking about this is going to factor to x minus 2 times x minus 1, right? So for our f of x. And so I'm going to get a y-intercept at x equals 2, or sorry, an x-intercept at x equals 2, and an x-intercept at 1. So I get here and here. My y-intercept is going to be positive 2 here, and that's going to reflect across here because my axis of symmetry is going to be at 1.5. And if we plug in 1.5, we're going to get negative 1/2 and positive 1/2. And so I get to this negative 1/4. And so my graph looks like such. Okay? Now, what does that mean for my inverse? Well, come back over here. This means that my y-intercept, if I make this 0, right? If I make the x equal to 0, I'm going to get that y minus 2, right? And then the y minus 1. So y is equal to 2, or y is equal to 1. So I end up with 2 blue dots here and here. And so my axis of symmetry is no longer a vertical line, but a horizontal line. Because now my x-intercept is at what? 2. And that reflects across over here to 2, 3. And my vertex would be at negative 1/4 and 1.5. And so I end up with this parabola here. So again, it's a little hard to see it here, just with the way these two functions kind of overlap very closely. But these y-intercepts here correlate to these x-intercepts here. Again, everything in the x's and y's is going to switch. Now, is the blue a function? No. And so we actually need to restrict our domain. And so how we're going to restrict our domain, in this case, we're going to restrict the domain of the original function, which will restrict the range of the inverse function. So I'm going to restrict the domain to points that are to the right of the original axis of symmetry. And so I'm going to restrict the original domain to 1.5 to infinity, which means that the range of my new function, my inverse function, would be from 1.5 to infinity. Because it's not that the values are going to change, it's that it was the domain of the original function, and it's the inverse, the range of the inverse, right? Because we're actually going to come across this way, right? And what's going to erase is the bottom part of this graph. And so we're not going to have that piece anymore. And this piece will also get erased. Not the blue part, just the orange part. Because this will still come through here, and go out that way. And so now we're only dealing with this piece of the orange and this piece of the blue. Now, if I've graphed this correctly, there's one property of inverses I want you to see. When these graphs intersect, the intersection point has to be where the x is equal to the y. Because think about it. If I'm going to invert this and switch that x and y, those values got to be the same. And so this intercept point is at about 3 and a partial and 3 and a partial. Again, we could go to our graphing calculator to figure out what that's exactly going to be, but that's where we're at. All right. So with that being said, that's example 3. So inverse functions, this is our last thing we're going to look at today. Two functions, f and g, are inverse functions if and only if both of their compositions are the identity function. And what we're talking about there is this statement here, that if I take f of g of x, I get x. And if I take g of f of x, it is also equal to x. You might have noticed that it said f of g there for a second. I just changed it because, again, I found that error when I copied it over and didn't switch the order of them. So again, f of g of x is equal to x, and g of f of x is equal to x. So what does that mean to a problem? Let's take a look at this last example that we have. Verify that two functions are inverses. Determine whether f of x equals 3/4 x minus 6 and g of x is equal to 4/3 x plus 8 are inverse functions. So what we're going to do is we're going to take both of these statements that we see here. And so I'm going to do f of g first, which means I'm taking the g function and plugging it into the f function. Because remember, f of g of x, what's the interior, what's the exterior function? So what I'm going to get is the 3/4 times the 4/3 x plus 8 minus the 6. And so distributing the 3/4, this becomes 12 over 12, which is just 1, so I get the x. And 3/4 of 8 is 6. And the minus 6 is still sitting out back. And so when we look at f of g of x, this cancels and we're left with x. Now, had this f of g of x not come out to x, I don't even try g of f, because it doesn't matter. They both have to come out to the identity of x. So let's do now g of f of x, which means I'm going to switch the order. I'm not going to do the g going into the f, I'm doing the f going into the g. So g of f of x is equal to, so I've got the 4/3, I'm plugging in the f function where I see the x, and then plus the 8 on the end. Distributing the 4/3, I get 12 over 12, which gives me 1, so that's just x. 4/3 of 6 is negative 8, and the plus 8 out back. Negative 8 and positive 8 will cancel, and so g of f of x is equal to just x. And so we get the identity for both, So are these inverses? Yes. F and G are inverses of one another because the composition f of g and g of f both equal x. And again, it's a really simple explanation because, again, if they're inverses, they've got to both come out to x when we do those compositions. And the answer would be no if either one or both don't equal to x. And again, normally what you're going to see is that you get the f of g not equally to x, and then you're done. All right, and so that's this lesson. Again, pretty short with 4 examples there. I know this is a 20-minute video at this point, but that's the basics of inverses. They're not difficult if you understand that all you're doing is switching your x's and y's. You're switching your domains and ranges. If you understand that, this is a very easy lesson to comprehend. If you try to make it more difficult than that, then you're just adding suffering and woe to yourself. So the word of the day is inverse. I-N-V-E-R-S-E, inverse is the word of the day, so make sure you get that submitted in, and I hope y'all have a great spring break.